Hi everyone. Today we're going to be completing our third and final method for solving exponential and logarithmic equations. First we talked solving exponentials and logs using inverse operations, then we talked solving by factoring, and today we're going to be talking solving by creating common bases, both logarithmic bases and exponential bases. To start, we got to go over some of these prerequisite skills, some of our exponent rules. So in number one, we have x to the fifth divided by x squared. When we divide exponents with the same base, we subtract the powers. So this is equal to x to the 5 minus 2. This is our quotient rule for exponents. 5 minus 2 is 3, so our answer is x cubed. Number two, again, we subtract these powers, but now we have a variable in the numerator in the power. So this is 7 to the x minus 2. This can't be simplified further. Number three, we're multiplying these. So when we multiply exponents with the same base, we add the powers. So this is equal to 4 to the x plus 3. Nothing to simplify there. And then number four, we have our power rule. We're raising a power to a power. And when we do that, we multiply those two powers together. So this is 9 to the x times 2, or 9 to the 2x. And the last one here, number 5, we multiply in the numerator. So we're going to add those exponents, 5 to the x squared plus 2x. And that's all over 5 cubed. So what we're going to do then is our quotient rule. We're going to subtract those powers. So this is equal to 5 to the x squared plus 2x minus 3. Okay. Let's take a look at some examples here. In number one, here we have 7 to the x minus 5 equals 7 to the 2x. First thing I notice about this problem is that these are exponents and they have the same base. So what we can do when we're setting them equal to one another is we can set those powers equal to one another. So if we have the same base, those powers are equal. So x minus 5 equals 2x, and then solving for x, we subtract x from both sides, x equals negative 5. Always go back for any of these types of problems to check and make sure that it fits within the domain. Because these are exponentials, the domain for exponentials is all real numbers, so negative 5 is certainly within that domain. So this is a solution. Example 2, we have our quotient rule on the left-hand side, so we're going to subtract those powers, 4 to the 6 minus x. And on the right-hand side, we have our power rule, so we're going to multiply those powers, a power to a power. So x times 2 is 2x. And then finally, we have that same base of 4, so we can set the powers equal to one another. 6 minus x equals 2x. Solving for x, we add x to both sides and divide both sides by 3. We get x equals 2. Let's try a few. Number 1, here we have e to the x squared equals e to the 16th. So our power rule on the left side, this is equal to e to the 2x equals 16, e to the 16th. And so what we can do is set those powers equal to one another. 2x equals 16. Dividing both sides by 2, we get x equals 8. Number 2, on the left-hand side, there's nothing to do here. This is already simplified. But on the right-hand side, we've got our quotient rule. Because we're dividing exponents with the same base, we can subtract those powers. So 15 minus x in the exponent. Common base is 10, so we're ready to set those powers equal to one another. 2x equals 15 minus x. Adding x to both sides, we get 3x equals 15. And then dividing both sides by 3, we get x equals 5. 5 is within the domain of the exponential. There's no issues here. Number 3, we already have the common base of e, so we can just set those powers equal to one another. X squared minus 3 equals 6. Adding 3 to both sides, we get x squared is equal to 9. And then square rooting both sides, we get x is equal to plus or minus 3. And finally, number 4, we're multiplying in the numerator, so we can add those exponents, 5 to the x squared plus 2x, and that's all over 5 squared. On the right-hand side of the equation, it's just 5. Now that we have a common base on the left-hand side in that fraction, we can subtract those powers using the quotient rule. So 5 to the x squared plus 2x minus 2, and that's equal to 5 to the first power. If there's nothing written, you can assume that power is 1. Because we have a common base now of 5, we can set those powers equal to one another. X squared plus 2x minus 2 equals 1. Subtracting 1 from both sides, we get x squared plus 2x minus 3 equals 0. And then we can factor x plus 3 and x minus 1 equals 0. And then finally, using the zero product property, we get x equals negative 3 and x equals 1. All right. At the bottom of the page, go ahead and check all of your answers for this first section. Okay, go ahead and flip the page. All right, so now we're going to practice with some logs. We're going to condense some of these expressions. So number one, first thing I noticed, that coefficient to 2, we can use our power rule for logs. So this is log base 3 of x squared, and then minus log base 3 of 4. And then we're subtracting these two logs of a common base, so we can use our quotient rule. This is log base 3 of x squared over 4. Okay. Number two, all of these are natural logs. So we have our power rule for the first one, natural log of x cubed minus natural log of y to the fourth plus natural log of z squared. First thing I notice is the quotient rule. So we can divide x cubed and y to the fourth. And then we're also going to multiply this by z squared. So in the numerator, we have natural log. In the numerator, we have x cubed, z squared, and that's all over y to the fourth. Okay. All right. Numbers 3 and 4, I just want to state the domain. What is the domain for each of these logs? For number 3, I notice that we have 3 minus x. Now remember the argument of the log, the parent function, has a domain x greater than 0. Okay? So that tells me that 3 minus x must be greater than 0. The argument of the log here must be greater than 0. So solving this inequality, we can subtract 3 from both sides. We get negative x is greater than negative 3. And dividing by negative 1, we get x is less than positive 3. Okay? Remember, dividing or multiplying any inequality by a negative, we have to flip that inequality. So the domain here is x is less than 3. Let's go ahead and use interval notation. So this would be from negative infinity to 3. Okay. For number 4, 2x minus 6 must be greater than 0. Adding 6 to both sides, 2x is greater than 6. And dividing by 2, x is greater than 3. All right, so the domain would be from 3 to infinity. Okay, let's check out a few examples. So here we have log base 3 of x minus 5 equals log base 3 of 2x. Just like exponentials, if we have a common base on both sides of the equation and there's nothing on the outside of those logs, we can just set the arguments of the logs equal to one another. So we get x minus 5 equals 2x. Solving for x, we subtract x from both sides, and we get x equals negative 5. Now we have to always go back and check, is negative 5 in the domain of these logs? If I were to plug in negative 5 here, would that cause a domain error? Would that cause the argument of this log to be outside the domain? And so what we can do is plug in negative 5 and see that the arguments of the log here would become negative 10. Because negative 10 is not positive, it's not greater than 0, we have no solution. So we eliminate this solution. This would be what's called extraneous, an extraneous solution. For example 2, again, we have these logs all base 5, but I noticed we're adding 2 of these here. So we've got our product rule. So we can multiply the arguments here, 2x times x, and we get 2x squared equals, so log base 5 of 2x squared equals log base 5 of 8. And then finally, because we have the same log base 5, we can set those arguments equal to one another. Dividing both sides by 2, we get x squared equals 4, or x equals plus or minus 2. We have to check both solutions x equals 2 and x equals negative 2 to see if either of them are extraneous. When we plug in 2, we find that the argument is just fine. It's positive. 2 times 2 is a positive number, and also 2 is a positive number. But when we plug in negative 2, it does cause the domain to be equal to negative 4 or negative 2, both of which are negative. That's outside the domain. So we have to eliminate x equals negative 2. So the only solution in this case is x equals positive 2. All right? Let's get some practice. So let's go ahead and solve this here. I noticed that these are both the common log. There's no base written, so we can assume it's log base 10. Because we have the same base, we can set those arguments equal to one another. X squared minus 4 equals 3x. Setting this equal to 0, we get x squared minus 3x minus 4 equals 0. And this factors to x minus 4 and x plus 1 equals 0. So I get the solutions x equals 4, x equals negative 1. Well, wait, let's go back and check if either of these are extraneous. Plugging in 4 back here, 4 squared minus 4, is that positive or negative? It's positive. Plugging in 4 here, 3 times 4, is that positive or negative? Also positive. So 4 is a solution. But plugging in negative 1 here, negative 1, the quantity squared, minus 4, that's positive. That's totally fine. Or I'm sorry, that's negative. 1 minus 4 is negative 3. Likewise, over here, 3 times negative 1 is negative 3. So negative 1 in both accounts fails the test here, so negative 1 is an extraneous solution. The only solution here is x equals 4. Number 6, I notice on the left-hand side we can use our power rule, so this is natural log of x squared equals, we've got our quotient rule, so this would be natural log of 18x over 2. Okay. So now we have x squared is equal to 18x divided by 2 is 9x. So I'm setting those arguments equal to one another. We've got the natural log on both sides. And then I'm going to subtract 9x from both sides. So we get x squared minus 9x equals 0. Over here, I'm going to move. Factoring out a GCF of x, we get x times the quantity x minus 9 equals 0. And we get two solutions, x equals 0, x equals 9. Let's check and see whether both of these work. Remember, the argument has to be positive. It can't be negative, can't be 0. So our first solution, x equals 0, if we plug it in here, both of these arguments equal 0, which the log cannot have an argument equal to 0. It must be greater than 0. If we plug in 9, that's totally fine. That's a positive quantity for both of these. So 9 is the solution, x equals 9. All right. You can check your work for any of these problems on this page right now. All right, let's get some more practice. So go ahead and flip the page, creating common bases to solve. So sometimes you won't have a common base and you're going to have to manipulate the equation in order to get that common base. So for example, 8 to the power of x equals 2 to the power of x plus 2 can be rewritten as 2 cubed. 8 can be rewritten as 2 cubed. Okay, so making a substitution for that 8 for 2 cubed, now we have that common base using our power rule. In the same way, both 9 and 27 are powers of 3, where 9 is a perfect square and 27 is a perfect cube of 3. So we can write both of these in terms of an exponential base of 3. And then again, we've got our power rule, so we can multiply those powers and then set them equal to one another. Let's use this method to solve the rest of these. So here we have 9 to the x squared equals 81 to the negative 2x minus 2. So first thing I notice is that both 9 and 81 are perfect powers of 3. 9 is equal to 3 squared, and then we're raising that to the x squared. And then 81 is 3 to the 4th. And then we're raising that to the negative 2x minus 2. You could also write this both in base 9, where 81 is 9 squared. You'll get the same answer either way. Using the power rule, we get 3 to the 2x squared is equal to 3 to the negative 8x minus 8. And then now we've got that same base, we can set those powers equal to one another. 2x squared equals negative 8x minus 8. And then setting this equal to 0, 2x squared plus 8x plus 8 is equal to 0. And then factoring out a GCF of 2, we get 2 times the quantity x squared plus 4x plus 4 equals 0. And this factors to 2 times the quantity x plus 2 the quantity squared. And so all we have here, we only have one distinct factor, variable factor. So we have x plus 2 equals 0, or x equals negative 2. All right. And again, negative 2 totally works because this is an exponential. So that's within the domain. Number 8, I notice that we have 1/2 to the power of x. That looks similar to 2 to the x minus 6, but instead of 2, we have 1/2. One way that we can write 2, or rewrite 1/2 as a power of 2, is 2 to the negative first power. Remember, the negative power is the reciprocal power, so that's going to flip our fraction. So then using our power rule, we have 2 to the negative x equals 2 to the x minus 6. And so we get negative x equals x minus 6. Adding x and adding 6 to both sides, we get 2x equals 6, or x equals 3. All right, we got 2 more for today. Number 9, we've got 5 to the 4 minus x and 1 over 125. Well, I noticed that 125 is a perfect power of 3, perfect power of 5, it's 5 cubed. And then it's also the reciprocal. So we can write this as 5 to the negative 3. Now that we have a common base, we can set those powers equal to one another. Adding x and adding 3 to both sides, we get x equals 7. Okay. And last one, I noticed that 1/2 is a perfect power of 2. It's 2 to the negative 1. And then 4 is also a power of 2. That's 2 squared. So we could write this as 2 squared, the quantity to the 2x minus 1, equals 2 to the negative 1, the quantity to the x. Using our power rule, 2 to the 4x minus 2 equals 2 to the negative x. And then we have 4x minus 2 equals negative x. Set those powers equal to one another. Adding x to both sides and then adding 2 to both sides, we get 5x equals 2, or x equals 2/5. And you can also check your work below. All right. These have been our notes on solving by creating common bases. Remember, you might have to manipulate some of these bases to look the same, perfect powers of 2, those logarithmic bases as well. Don't forget to check for extraneous solutions. Does it fit within the domain? We're going to get a lot of practice, so we'll see you tomorrow. Have a great day, everybody. Goodbye.